Everyone, we're going to wrap up chapter 16 in this video. So the chapter on conjugated pi systems and pericyclic reactions. So last time we were discussing the Diels Alder reaction and we got to stereochemistry, and we said that if your electron withdrawing groups on the dienophile are cis to each other, then they'll also be cis to each other in the product. But because they'll be cis to each other in the product, we end up forming a meso compound, at least if everything is symmetrical. We also talked about a situation where the electron withdrawing groups were trans to each other, so we would draw one as a wedge and one as a dash in the product. And that means that we would also have an enantiomer, so a non-superimposable mirror image. Now, in this example, I said that one cyanide was pointing out and one was pointing in. So that does make a difference in how you draw your product. So that's going to lead me into endo versus exo addition. Okay, so let's look at an example. And this one is from your textbook, so if you want to go back and kind of look at those figures, you can. So let's say that we have, oops, I already drew it wrong. Let's say we have our diene, and our dienophile has two cyanide groups attached, and they're cis to each other. So we could actually end up with two different products. Now, remember from last time we talked about how in a Diels Alder reaction we end up forming a boat conformation. So in this reaction, that is similar. So we are going to form that same boat conformation. Now in this one, we do have this kind of triangle or one carbon bridge attached to our diene. That is going to point above the plane. And then we have our electron withdrawing groups. So those could either be in axial positions, just pointing down, or they could also form, and your textbook has better drawings of all this. It's hard to draw these, so it's okay if you are struggling with drawing these as well. But they could also be kind of in like an equatorial position, so to speak. So kind of pointing up. So the situation where the cyanide groups are pointing downward is called endo. And the situation where the cyanide groups are pointing upward is called exo. Okay. So let's draw the transition states that can produce these two products. So let's draw the endo transition state. So what happens in a Diels Alder reaction is that the diene is actually going to sit kind of above the dienophile. So it's almost like a UFO coming in to beam up the dienophile. So let's see if I can draw that accurately or well enough so that it's easy to see what's going on. Oh, and actually, I'm going to draw these double bonds a little differently. Okay, so let's look at the endo scenario. So in the endo scenario, the cyanide groups are actually going to kind of face inward. So we've got our pi electrons delocalized around the diene, and then they start to make new bonds with the dienophile down below. So this is our transition state for the endo product. And again, that dienophile is lined up below the diene. Now let's look at the exo scenario. So we would still have our diene up above, but this time the cyanide groups are going to be pointing away from the diene. All right, so we've got our delocalized electrons, we're forming bonds, breaking bonds. And that's our exo scenario. Okay, so which one is more favorable? Well, it's kind of hard to tell, right? You might think, oh, well, wouldn't it be favorable for the cyanide groups to kind of face away from everything since they're electron withdrawing? But in actuality, it's more favorable for the electron withdrawing groups to face towards the diene. So there's a favorable interaction between the developing pi bond on our ring. Oh, let me actually highlight it in blue. And these electron withdrawing groups. So the electron withdrawing groups help to kind of stabilize that transition state. And I'll show you a figure in a bit about what's going on there. But that means that the endo product is going to be the major product. And then the exo product is a very minor product. Okay, so let's actually skip ahead a little bit. I wanted to show you this slide because this will demonstrate a little bit about why the endo transition state is more stable, and then why the endo product is favored. So in this example, we have that same diene that I drew before, but this time our dienophile is a little bit different. Oh, I ran out of room, but there's two carbonyl groups on either side. And if we look at the endo scenario, and we replace each of these carbons here with pi or p orbitals, notice that this is the highest occupied molecular orbital for our diene. And then looking down below, we have the LUMO, or the lowest unoccupied molecular orbital for our dienophile. And then also notice that we have overlapping between the red lobes and then overlapping between the blue lobes, which is what we want. But look in the back. So if we look at the back, we can see that those red lobes are overlapping with the electron withdrawing groups. Same for the blue lobes. So we have two interactions. But if you look at the exo scenario where the electron withdrawing groups are facing away from the reaction, we only have one overlapping area, and that's where the reaction, the Diels Alder reaction, is occurring. So if the electron withdrawing groups can kind of overlap with the p orbitals from the diene, then that stabilizes the transition state, and that will give us the more stable product, which is the endo product. Okay, so this might be a little confusing, but at the end of the day, just remember the endo product is the favored product. So it's more stable for the electron withdrawing groups to face inward toward the reaction. Okay, so let's actually look at some examples. So I'm going to go back. All right, so let's look at an example where we have our same diene that I drew before. And then our dienophile is going to look kind of similar to one we've seen before. In fact, this is the one that we used in our Diels Alder reaction in lab. Okay, so this entire part of the dienophile is our electron withdrawing group, which is kind of cool. So we don't have two separate electron withdrawing groups, we just have one, and it's all connected. Okay, so let's try to draw the transition state. And remember that the endo transition state is the more favorable transition state. So see if you can pause the video and try this on your own first. And when you're done, we'll go over the transition state together. Okay, so don't worry if your drawing looks a little funky. I have trouble drawing this as well. But maybe you're an artiste and you are much better at drawing than I am. I don't know. All right, so let's draw our dienophile down below, and we want to make sure that that electron withdrawing group is facing inward towards our diene. Oh man, this is hard. Okay. I'm trying to kind of draw it sideways. All right, and then we've got delocalized electrons. They're going to come down and form bonds. Oh, I forgot my methyl group. Oh. Oh, geez. Okay, I'm going to try to redraw this. This is tough. Again, don't feel bad if you can't draw this. I'm struggling too, obviously. Let's see. Maybe I'll try it so that it's a little more separated. Okay, there we go. That's a little better. Okay, so now we can kind of see the interactions. And you can kind of see how the nitrogen and those carbonyl groups are sort of lined up with the back part of our diene. And so those are kind of stabilizing that double bond that's forming in the back. All right, so again, it's okay if your drawing is a little wonky, that's fine. Okay, so now let's draw what this would look like once all of our new bonds have formed. So again, we're forming a boat conformation. It's almost kind of like a folded piece of paper there. We have our double bond that formed in the back. So for instance, if we draw those same arrows that we've been drawing up above, the double bond that's going to form here is right there. All right, now we have to also take into account this bond here. Where is that going to go? So that is going to get pushed upward. And then we have our electron withdrawing group, and that's going to all point downward in the endo position. Points downward. Okay, so now let's draw this in the two-dimensional form with wedges and dashes. Okay, so we've got our cyclohexene that forms. So again, we've got our double bond that forms on the backside there. And then what about our little triangle, the green triangle there, the one carbon bridge? Well, that is pointing upward across this cyclohexene ring, so we'll just draw some wedges here. Okay, so again, that is our triangle. All right, and then we have to draw our electron withdrawing group. So we said it's pointing downward, and if something points downward, then that means it's going to be pointing away from us. So it will be in a dashed position. So if something is pointing down, that equals a dash. Or the other way that we could say this is if it's pointing outward, then it's a dash. Okay, so again, this is the endo product. And we drew the endo transition state. Okay. Oh, and let me just highlight our electron withdrawing group so we can keep track. So let's do another example. Let's show one where we have some groups pointing in and some pointing out. So this is our diene. And let's say we have a methyl group that's kind of pointing in, and then a methyl group that's pointing out, plus our dienophile, which will have two cyanide groups that are both pointing out. Okay, so just a hint, if something is pointing out, that means it's going to be in a dashed position. If something is pointing in, that means it's going to be in a wedge position. So see if you can figure out the product, and I encourage you to also draw the transition state down below to kind of get an idea of where everything is going to point. So pause the video, try this one on your own first, And then when you're done, we'll go over it together. Okay, so let's draw the transition state. Let's see what's going on here. So we've got our diene. We have one methyl group kind of pointing out, one pointing in. And we have our dienophile, and we know that the endo configuration is more favorable. So we'll draw the cyanide groups kind of pointing inward. And then we'll draw our delocalized electrons, and we're forming new bonds, breaking old bonds. Okay, so then we know we form that boat conformation with a double bond at the backside there. And now we have to figure out, where do all of these substituents point? Where are they pointing towards or away? So the cyanide groups, we said, were in the endo position, so that means they're going to point downward. We also said that one of the methyl groups was pointing out or away, so we'll just draw that kind of going out. So maybe that's in kind of a downward equatorial position. And then the other methyl group was kind of pointing inward. So that might be in more of like an axial position, kind of in towards the molecule. Now, this is confusing, so it's okay if you're a little lost. So let's just draw this in the two-dimensional form. Okay, so we know that as usual, we're going to form two new bonds between our diene and our dienophile. And we're going to move one of our pi bonds over. So we get cyclohexane. So that's normal, that's usual. We've seen that a lot now. And then the cyanide groups we said are pointing out. So that must mean they're in the dash position. Okay. Now, the methyl group on top is pointing out as well, so that will also be in a dash. And then the other methyl group is pointing in, so that must mean it's in a wedge. And if we look down below at our three-dimensional structure, we can see that the methyl group that was pointing out is kind of in that outward position. The methyl group that was pointing in is pointing up. So it's in a wedge position. So I don't know if the three-dimensional drawings are helping at all, but if you're feeling a little lost with the 3D stuff, that's okay. Just remember that if groups are pointing out, there'll be a dash on the product. If they're pointing in, they'll be in a wedge in the product. That's the key part. Okay. And then here's that endo versus exo slide again. And let's see. Oh, we're actually going to skip this example slide. And let's go to one last topic before we end this chapter, and that's Diels Alder Regiochemistry. Okay, so regiochemistry, remember, tells us where groups will be positioned at the end of a reaction. And so far, we've been dealing with symmetrical reactants. But what if we have asymmetrical reactants? Okay, so if we have asymmetrical reactants, we have to figure out, what's the best position for all of these substituents. So, for example, let's say we start with the following. Okay, so we have a methoxy group attached to our diene, and our dienophile is going to have an aldehyde bonded at the top, and then just a simple methyl group bonded at the bottom. Okay. So there's a couple of different outcomes that could occur. We could end up with our aldehyde and our methoxy group just kind of in the same positions that we drew them in initially. Or we could end up with one of them flipping. So for instance, if we flipped our diene so that the methoxy group was on the bottom. Okay, so these are our two possible outcomes. Now, what's interesting is that the second product we drew is the major product. The first one we drew is the minor product. Okay, so why? Why is the bottom product the major product? Well, let's look at where the electrons go. So I'm just going to erase this and we'll go over the electrons and where they're moving to and away from. So we do have some resonance structures here. So in our first reactant, the diene, one of the lone pairs from oxygen can move down to form a pi bond, and our pi electrons that are next door can move over onto carbon. So now we have a positively charged oxygen and a negatively charged carbon. Okay, let's look at our aldehyde, because we could also draw resonance structures there. So for example, we can move pi electrons up to oxygen. So now we have a negatively charged oxygen and a positively charged carbon. And then we can also move the pi electrons next door so that we get, or so that we move the positive charge to another carbon. Okay, so what we actually have here, if we draw the hybrid structures, we have delocalized electrons across the top two bonds on our diene. So there's a partial positive charge on oxygen, a partial negative charge on carbon. And in our aldehyde example there, we have delocalized electrons going from the second to last carbon all the way up to oxygen. So oxygen has a partial negative charge. The carbon below it has a partial positive charge. And then the carbon at the end also has a partial positive charge. Okay, so the most stable product is going to form when the partial negative charge on the diene is aligned with the more partial positive charge of the carbon on the dienophile. Now there is that other partial positive carbon up above, but that's right next to a partial negative oxygen. So the partial positive carbon at the bottom of the molecule is more isolated, and so it's going to be more stable to flip our diene and line up the partial negative carbon with the partial positive carbon. Okay, so now what's going to happen is that pi bond can move over, create a bond. Oops. Oh no, I went back too far, sorry. And then this pi bond will move over. And then the final pi bond there will move over and we'll create our final product. Okay, now I'm actually going to redraw some of this up above. Actually, let me just erase it and redraw it. So the other way that you could draw all this which might make more sense, you can draw the original two products, or reactants, but just remember that we have a partial negative and partial positive there. So that's another way to look at it too. Okay, so now we have to figure out in our final product, where are all of the groups going to be positioned in terms of wedges and dashes? So what's the stereochemistry? Okay, so let's look at the aldehyde group. Is the aldehyde pointing out or in? Out, because it's pointing away from the reaction. All right, what about the methyl group on that same molecule? Is it pointing in or out? In, towards the reaction. Okay, and then what about that methoxy group? Well, that doesn't really matter because it's going to be on a double bond, so it doesn't have any stereochemistry. Okay, so in our final product, we have our cyclohexene ring. Again, the methoxy group is on a double bond or an sp2 hybridized carbon, so it's not going to be in a wedge or a dash, it'll just be planar. But we know the aldehyde group is pointing out, which means it will be in a wedge. And we know that the methyl group is pointing in, so it will be, oh, sorry, the aldehyde will be in a dash, excuse me. The methyl group will be in a wedge. So remember, out is a dash, in is a wedge. So let's just write that. Out equals dash, in equals wedge. I apologize for getting those mixed up. It's easy to do. All right. So we've gone over a lot in this lecture. We talked about exo versus endo configurations, and we said that endo transition states are more stable. So it's more stable for the electron withdrawing groups to kind of face inward. So typically they'll end up as dashes. And then we also said here with regiochemistry, we want to make sure that the negative end of one molecule is aligned with the positive end of the other molecule, and then we can form our cyclohexene ring. Okay. So that's the end of chapter 16. I will try to post a worksheet that goes over some of these problems, and I'll also post the key so you can check your work. And if you have any questions, you can set up an office hour with me, or you can also just email me or message me through Canvas. All right, good luck.